According to the National Electrical Code, the size of the neutral conductor in a 110/240 volt single-phase residential service and feeder must be the same size as the ungrounded conductors. This is due to the function of the neutral conductor in carrying the unbalanced current between the phases. To understand this requirement fully, we need to delve into the principles of electrical distribution and the specific provisions outlined in the National Electrical Code. The National Electrical Code, or NEC, serves as the definitive standard for safe electrical installations in the United States. It's a comprehensive set of guidelines intended to protect people and property from electrical hazards. The NEC addresses virtually every aspect of electrical wiring, from conductor sizing to overcurrent protection to grounding and bonding. It is updated every 3 years to reflect the latest technological advancements and safety practices. Compliance with the NEC is essential for ensuring electrical safety and code compliance. In a 110/240 volt single-phase system, which is commonly found in residential settings, power is delivered using 2 ungrounded conductors, often referred to as hot wires, and 1 grounded conductor, which is the neutral. The 2 ungrounded conductors each carry 110 volts with respect to the neutral, but they are 180 degrees out of phase with each other. This phase difference allows for the delivery of 240 volts between the 2 ungrounded conductors. The neutral conductor serves as the return path for current from both of the 110 volt circuits. Ideally, in a perfectly balanced system, the current flowing through each of the 110 volt circuits would be equal, and the neutral conductor would carry little or no current. However, in reality, electrical loads are rarely perfectly balanced. This means that the current flowing through one 110 volt circuit may be different from the current flowing through the other 110 volt circuit. The difference in current between the 2 circuits is known as the unbalanced current. The neutral conductor is responsible for carrying this unbalanced current back to the source. If the neutral conductor is not properly sized, it may overheat due to the excessive current flow. This overheating can lead to insulation damage, fire hazards, and even electrical shock. Therefore, the NEC mandates that the neutral conductor must be sized to safely carry the maximum unbalanced current that is likely to occur in the system. The specific requirements for neutral conductor sizing are outlined in NEC Article 220.61, which addresses feeder and service neutral load calculations. This article provides detailed guidelines for determining the minimum size of the neutral conductor based on the characteristics of the electrical loads being served. One of the key considerations in neutral conductor sizing is the type of loads being served. For example, if the system primarily serves resistive loads, such as lighting and heating, the unbalanced current is likely to be relatively small. In this case, the NEC permits a reduction in the size of the neutral conductor under certain conditions. However, if the system serves a significant amount of nonlinear loads, such as electronic equipment and appliances with electronic power supplies, the unbalanced current is likely to be much larger. Nonlinear loads generate harmonic currents, which are multiples of the fundamental frequency of the electrical system. These harmonic currents can significantly increase the current flowing through the neutral conductor, even if the system appears to be relatively balanced. In such cases, the NEC requires the neutral conductor to be sized to carry the full calculated neutral load without any reduction. For 200 amps residential service, the ungrounded conductors are typically sized to 4/0 American wire gauge copper or 250 kc mil aluminum, assuming the use of 75°C termination rated conductors. The NEC requires the neutral conductor to be the same size as the ungrounded conductors in most cases, especially for residential services. This means that the neutral conductor would also need to be 4/0 American wire gauge copper or 250 kc mil aluminum. There are limited exceptions where the neutral conductor size can be reduced, but these exceptions are typically not applicable to residential services. One exception is for services with a demand factor of less than 70% for the neutral load. However, this exception is rarely used in residential applications because the demand factor for the neutral load is typically much higher than 70%. Another exception is for services with a neutral load that consists primarily of nonlinear loads. In this case, the NEC permits the neutral conductor to be sized at 100% of the nonlinear load plus 70% of the remaining load. However, this exception is also rarely used in residential applications because the nonlinear load is typically not a significant portion of the total load. It is important to note that even if the NEC permits a reduction in the size of the neutral conductor, it is always a good practice to err on the side of caution and use a neutral conductor that is the same size as the ungrounded conductors. This will help to ensure that the neutral conductor can safely carry the maximum unbalanced current that is likely to occur in the system. In addition to the NEC requirements, there may also be local codes or regulations that govern neutral conductor sizing. It is important to check with the local electrical inspector to determine if there are any additional requirements that must be met. It is also important to consider the voltage drop in the neutral conductor. Voltage drop is the reduction in voltage that occurs as current flows through a conductor. Excessive voltage drop can cause equipment to malfunction and can even damage electrical components. The NEC recommends that the voltage drop in the neutral conductor should not exceed 3%. To minimize voltage drop, it is important to use a neutral conductor that is large enough to carry the expected current without excessive voltage drop. The NEC provides guidance on voltage drop calculations in Informative Annex C. These calculations can help determine the appropriate size of the neutral conductor to minimize voltage drop. Furthermore, it is essential to ensure that the neutral conductor is properly connected at all termination points. Loose or corroded connections can create resistance, which can lead to overheating and voltage drop. All connections should be cleaned tight and properly torqued according to the manufacturer's specifications. The use of appropriate antioxidant compounds can also help prevent corrosion at connection points. Grounding and bonding are also critical aspects of electrical safety. The grounding system provides a low impedance path for fault current to return to the source, which helps to trip over current protective devices such as circuit breakers and fuses in the event of a ground fault. The bonding system connects all metal parts of the electrical system together, which helps to equalize the voltage potential and prevent electrical shock hazards. The NEC provides detailed requirements for grounding and bonding in Article 250. These requirements must be followed to ensure electrical safety. In summary, the NEC requires the neutral conductor in a 110/240 volt single-phase residential service and feeder to be the same size as the ungrounded conductors in most cases. This requirement is intended to ensure that the neutral conductor can safely carry the maximum unbalanced current that is likely to occur in the system. While there are limited exceptions where the neutral conductor size can be reduced, these exceptions are typically not applicable to residential services. It is always a good practice to err on the side of caution and use a neutral conductor that is the same size as the ungrounded conductors. In addition to the NEC requirements, it is important to check with the local electrical inspector to determine if there are any additional requirements that must be met. It is also important to consider the voltage drop in the neutral conductor and to ensure that the neutral conductor is properly connected at all termination points. Finally, it is essential to follow the NEC requirements for grounding and bonding to ensure electrical safety. Now, let's discuss some additional considerations related to neutral conductor sizing and installation. Firstly, consider the impact of future load growth. Electrical loads in residential buildings tend to increase over time as homeowners add new appliances, electronic devices, and other electrical equipment. It is important to anticipate this future load growth when sizing the neutral conductor. If the neutral conductor is sized too small, it may need to be replaced in the future to accommodate the increased load. This can be a costly and disruptive undertaking. Secondly, remember the importance of proper wire management. The neutral conductor should be neatly organized and properly supported throughout its entire length. Avoid sharp bends or kinks in the conductor, as these can create stress points and reduce the conductor's ampacity. Use appropriate cable ties or supports to secure the conductor to structural elements. Thirdly, never compromise on the quality of the conductors. Use only conductors that are listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories UL. Ensure that the conductors are properly rated for the voltage and amperage of the system. Using substandard conductors can create safety hazards and increase the risk of electrical failure. Fourthly, always follow the manufacturer's instructions for installing electrical equipment. Electrical equipment is designed to be installed in a specific manner, and deviating from the manufacturer's instructions can void the warranty and create safety hazards. Pay close attention to the torque requirements for terminal connections and use a calibrated torque wrench to ensure that connections are properly tightened. Fifthly, consider the use of surge protection devices. Surge protection devices (SPD) protect electrical equipment from voltage surges which can be caused by lightning strikes, utility switching, or other transient events. SPD are available in a variety of types and sizes, and they can be installed at the service entrance, at branch panels, or at individual pieces of equipment. Sixthly, remember to label all electrical panels and circuits clearly. Clear labeling makes it easier to identify circuits and troubleshoot problems. Use a permanent marker or label maker to create labels that are easy to read and understand. Include information such as the circuit number, the area served, and the type of load. Seventhly, conduct regular inspections of the electrical system. Regular inspections can help identify potential problems before they become serious. Look for signs of damage, such as cracked insulation, loose connections, or corrosion. Test the operation of ground fault circuit interrupters (GFCIs) and arc fault circuit interrupters if sized to ensure that they are functioning properly. Eighthly, understand the importance of electrical safety training. Electrical work can be dangerous, and it is important to have the necessary training and experience to perform electrical tasks safely. Consider taking an electrical safety course or apprenticeship program to learn about electrical hazards and safe work practices. Ninthly, be aware of the dangers of working with electricity near water. Water is a good conductor of electricity, and contact with water can significantly increase the risk of electrical shock. Always turn off the power before working on electrical equipment near water. Use ground fault circuit interrupters (GFCIs) to protect against electrical shock hazards in wet locations. Tenthly, never attempt to repair electrical equipment that you are not qualified to repair. Electrical equipment can be complex and dangerous, and attempting to repair it without the necessary knowledge and skills can create a safety hazard. If you are not qualified to repair electrical equipment, hire a qualified electrician to do the work. By following these additional considerations, you can help ensure that your electrical system is safe, reliable, and code compliant. Electrical safety is everyone's responsibility, and it is important to take the necessary precautions to protect yourself and others from electrical hazards. Furthermore, consider energy efficiency when making electrical decisions. Energy-efficient appliances, lighting, and other electrical equipment can save you money on your utility bills and reduce your carbon footprint. Look for products that are labeled with the Energy Star logo, which indicates that they meet certain energy efficiency standards. Use LED lighting, which is much more energy efficient than incandescent or halogen lighting. Install a programmable thermostat to automatically adjust the temperature in your home based on your schedule. Unplug electronic devices when they are not in use, as they can continue to draw power even when they are turned off. And finally, properly insulate your home to reduce heat loss and energy consumption. By making energy-efficient choices, you can help to reduce your energy consumption and save money on your utility bills. In conclusion, the neutral conductor in a 110/240 volt single-phase residential service and feeder is a critical component of the electrical system. It must be properly sized, installed, and maintained to ensure electrical safety and code compliance. The NEC provides detailed requirements for neutral conductor sizing and installation, and it is important to follow these requirements carefully. By understanding the principles of electrical distribution and the specific provisions outlined in NEC, you can help to ensure that your electrical system is safe, reliable, and energy efficient. And remember, when in doubt, always consult with a qualified electrician.